Hey everyone, and welcome. I'm here to be your chemistry tutor, and today we're going to tackle one of the trickiest topics in the SPM syllabus, carbon compounds. We're going to make it simple, clear, and get you totally ready for your exams. All right, let's kick things off with a super common problem. Picture this. You're in the exam hall, the clock's ticking, and you get a question about alkanes and alkenes. You know how it is. The pressure's on, and suddenly they all kind of look the same. Well, today we're going to make sure that never ever happens to you again. Okay, but before we dive in, I've got a secret weapon for you. As soon as we're done here, you can immediately put what you've learned to the test with real past year questions. Just scan this code, pop over to MCQ SPM.com, or grab the app. Trust me, it's the best way to make sure all this stuff actually sticks. All right, let's get right into it. To really get a grip on these two hydrocarbon families, we have to start with the one single fundamental thing that makes them different. And pretty much everything else we talk about today, it all comes back to this one core difference. So this table gives you a great snapshot, but the most important thing to focus on here is bond type. See how alkanes have only single carbon-to-carbon bonds? That makes them saturated. Alkenes, though, have at least one double carbon-to-carbon bond, which makes them unsaturated. This single detail dictates everything else, even how they burn. You'll notice alkenes are more sooty. And why is that? Well, it's because alkenes have a higher percentage of carbon in them. So when you burn them, they don't always burn completely, and that leftover carbon, that's the soot you see. Okay, let's think about this with an analogy. I want you to imagine an alkane is like a bus that's completely full. Every single seat is taken, in this case by a hydrogen atom. All the bonds are single, which means they're really strong and stable. The bus is totally saturated. No more room, it's not looking for any new passengers. Now an alkene, that's a completely different story. This bus has a pair of empty seats just waiting to be filled. And that double bond, that's our pair of empty seats. It's unsaturated, which makes it way more reactive, just waiting for new atoms to come and hop on board. That double bond is where all the action happens. So, what's the big deal about these seats, right? Well, it all comes down to how they react chemically. It really boils down to two main types of reactions. Are you swapping passengers, or are you just adding new ones? Remember our alkane bus? It's jammed-packed. So if someone new wants to get on, what has to happen? Exactly. Someone else has to get off. One of the hydrogen atoms has to leave so a new atom can take its place. We call this a substitution reaction. It's a simple one-for-one swap. So let's see this in action. Methane meets chlorine gas. But here's the catch. They'll just sit there next to each other until you give them a little push. And that push is energy, in this case from UV light. That energy is enough to break the bond between the chlorine atoms. Then, a free chlorine atom can come in and swap places with a hydrogen atom, giving us our final product, chloromethane. But with our alkene bus, oh, it's so much easier. It's got those empty seats, remember? Thanks to that double bond. So when a new molecule shows up, the double bond just opens up, and the new atoms are added right on. Nobody has to get kicked off the bus. Simple as that. And the classic example of this is something called hydrogenation. We're adding hydrogen gas to an alkene like ethene. That reactive double bond breaks open, the hydrogen atoms fill those empty seats, and just like that, you've turned an unsaturated alkene into a saturated alkane, ethane. Okay, so we've got the theory down. Now for the fun part. Let's see how we can use this to absolutely crush some real SPM questions. Because knowing the concepts is one thing, but applying them when it counts is the real skill. Check this out, a perfect example from a past paper. This is that hydrogenation reaction we were just talking about. They give you the equation. C2H4 plus H2 gives you C2H6. So, the question is, what are catalyst X and temperature Y? Take a second, see if you remember. Yep, the answer is nickel at 180 degrees Celsius. And this is a classic trap. So many students know the reaction is hydrogenation, but they blank on the conditions. The examiners know this, and they love to test these little details. So do yourself a favor. Make a flashcard for this one. Hydrogenation of alkenes, nickel, 180 degrees. Got it? All right, next up, a calculation question. I know these can look a bit scary, but they are totally doable if you just follow a system. This one's about the combustion of ethane. The absolute key here is, don't panic, just breathe and follow the steps. The final answer you should get is 0.56 decimeters cubed. And for pretty much any of these calculation questions, the game plan is always the same. Listen up. Step 1, find the moles of what they gave you. In this case, CO2. Step 2, use the mole ratio from the balanced equation to find the moles of what you're looking for. And finally, step 3, convert those moles into whatever they're asking for, which is volume here. Easy. Okay, one more for good measure. Look really closely at this equation. We start with methane, CH4, and end up with CH3Cl. A hydrogen is gone, and a chlorine has taken its place. Think back to our bus analogy. What's happening here? Is someone being added or is someone being swapped? You got it. It's substitution. You can see it clear as day. One atom is being replaced by another. That is the signature move of an alkane, right? Since its bus is already full, it has to swap. Okay, so now let's zoom out a bit, because in organic chemistry, nothing exists in a vacuum. Everything is connected. It's like this giant chemical roadmap where you can travel from one type of compound to another using a series of reactions. This flowchart here, this is your map. Let's follow one of the routes, shall we? We can start with an alkene, add some steam, and boom, we've made an alcohol. From there, we can oxidize that alcohol to make a carboxylic acid. Or we could even go backwards and dehydrate the alcohol to get our alkene back. It's all connected. Okay, guys, pay attention, because this slide right here is pure gold for your revision. These are the absolute key pathways you have to know. And look closely, each one has specific conditions, like catalysts, temperatures, and other chemicals. Seriously, knowing these details, that's what separates the good students from the great ones. All right, to wrap things up, I want to leave you with a little something to think about. We've seen how all these compounds are linked. So if you were a chemist and you could only start with one of them, an alkene, an alcohol, or a carboxylic acid, which one would you pick? Which one is the most versatile starting point? Have a think about that, and of course, don't just think, practice. Head over to mcqpm.com and really lock in this knowledge. All right, happy studying.